jump right into it. You can see our two experts, Chris Blundy and Tom Kinney. That's how they appear on my screen. Um, when I ask them the first question, they'll probably give a brief little introduction about themselves. I'll start with Tom, who I'm happy to see he is a geologist, which is always good. And the first question I have for Tom is quite simple. Um, I've heard now for more than 20 years trying to be a thermal provider, trying to be an expert in thermal. I always hear it is too expensive. You know, we've still done more than 200 projects, but we always get that why it's so expensive. So
35 plus years of experience. I work for GHD. I've been with GHD for quite some time, probably 18 years. Have been involved with a lot of complex site investigations and site remediation, which is a lot of fun. It keeps me excited, makes me want to come to work every day. I had a call with Gorm recently where he was talking about cleaning up the dirt. And as a geologist, I don't like to call it dirt typically. I told him, are you talking about soil? So we got that straight. But anyway, that's a little background on myself. So as far as the question though, is thermal remediation expensive? A lot of people don't want to use it because it's expensive. However, you need to look at what those costs depend on. And it depends on your project goals. I mean, that's number one right there. Those project goals can be based on these following three items, which could be your remediation target levels. Those target levels can drive ultimately how you're going to remediate the site. Do you need to get down to very low state or federal EPA numbers such as MCLs or soil cleanup criteria? Schedule and timing is another very important one. One of the advantages of thermal is that it's very quick. So you can get a 99% plus reduction in your contaminants of concern in the soil, and you can also do it quicker than most other technologies. So those are some of the advantages. And then you compare it to those other alternatives on each project, on a project by project basis. If you're doing a very small project and the levels are not that high, it's not the technology. But if you have a more complex project, especially with high concentrations or large areas of contamination, you want to take this into consideration. So item 3 here, the cost versus other alternatives, leads into another slide that I've got here, which for one specific project, we looked at these alternatives in order to select a remedy. And this was an area that had extremely high concentrations of CVOCs or chlorinated volatile organic compounds. And in particular, we had significant DNAPL. We also had LNAPL, high concentrations of dissolved phase and impacts in the vadose zone. So kind of a little bit of everything. And we looked at these different technologies. And in this case, the in situ thermal was significantly less expensive than the others. Our client wanted to focus on items 4 and 5 there. 5 actually had more, I guess, variability, not knowing what we're going to get into when you start excavating. You're talking about soils that are characteristically hazardous and you're going to have to dispose of. You're going to have to treat those before they're disposed. You also have both DNAPL and LNAPL coming in that you're going to have to haul off site. So you're dealing with a lot of unknowns when you start excavating that. So we had estimated at 150 and I put a plus next to that for the unknowns. So those were the numbers we had on that specific project. So I think that's kind of a reason as to why to consider using thermal, and that it's not always the most expensive. Sometimes it's the least expensive alternative based on your project goals.
all right, thank you very much. Chris, maybe a little bit about yourself. I know you're now in a sales role, but I know that you actually know technical stuff as well. So if you introduce yourself, and then, you know, the first question for you is essentially how does a typical in situ thermal project cost kind of break down? How much does each line item cost, and why is it typically, you know, more than $500,000 and often multi-million-dollar projects?
Yes. So I've been with TRS about 18 years. I met them at their first project, which was in Charleston, South Carolina. I was working for the oversight consultant, and being their first system from starting the new company, it had a lot of issues that I ended up having to fix for them since I was local, and I got pretty good at it. So I came on board towards the end of that project, and then stayed within the operations group until recently. And about a year ago, I moved over into business development and pricing and research and development optimization, things like that. But the if yeah, so the typical cost is pretty variable, and we'll get to that in another slide. But drilling and energy, as you can see, are two big numbers, um, and those are all driven by the situation. A lot of times we have to put these systems in where other systems can't go, near operating buildings, active facilities, and there's a lot of unique construction that has to be implemented in order to get those systems in. But this general schedule or percentage of total cost spans out over typically a year to a year and a half. Obviously, the big ones take a little more time than the small ones just to install. But the general time frame for most heating, the heating portion is 3 to 5 months, depending on the contaminant and the goals. Um, Head to the next slide, please. So we wanted we went back and we've been tracking the general price of our projects over time, and we thought this figure was a good representation of that. As you can see, economy scale is very important. This is the average for above and below 10,000 cubic yards. But again, it's very situational. The more difficult the contaminant to remediate, the price goes up because it increases time. And obviously, the bigger the volume, it increases time as well to install, and not really to remediate, but just to get the system in. And so those three cost drivers, it's kind of changed over this period. It's just the systems keep getting larger and larger. When I started out, 18 years ago, the systems were relatively small, a lot of pilot tests, 6, 7, 8, maybe 10 electrodes. Now we're consistently in the hundreds, and that just goes to show what Tom talked about a minute ago, is that its ability to achieve those goals has increased its popularity over time.
Okay, thank you. I have another one for you, Tom. I know you managed a large site recently where some of it was treated with thermal technologies and other areas were treated with other techniques. Can you tell us about that a little bit, and how you determined where thermal treatment was going to be done and versus other things?
Sure. Yeah, so as Gorm mentioned, this was a site that I worked on recently here. And it's a large, complex site, large, complex project, multiple source areas. The colors here show you the reds and the yellows that I struggle with a little bit, being colorblind, but that's what they tell me it is. The reds and the yellows are the higher levels of impacts based on membrane interface probe investigation. And then we also did detailed LIF work and traditional soil sampling and groundwater monitoring also. But based on those studies that we performed to come up with our conceptual site model, we looked at thermal along with other potential remedies for this project. And as far as how you come up with your remedial technology, I guess one other thing before going on to the next slide is really I just wanted to mention that some of these areas are so extensive that just one of the 12 areas by itself would be larger than the vast majority of the thermal projects. So there's some fairly significant areas both laterally and vertically out here. If we go on to that next slide, I think I can get into a little more detail there on how we selected and what we selected. So we looked at probably 20 different possible remedies out there and combinations of remedies and cost those out and looked at benefit analysis, both from a technology and from a cost perspective, and the client's goals from a timing perspective. Timing was important in this case. So we have a few different areas out there. On the far left, you can see where we have a shallow zone, generally 0 to 15 feet, close to the property boundary. Typically, the soils are heavily impacted, but in most cases, below characteristically hazardous numbers. And those areas we selected to just do your standard soil excavation and dewatering for any shallow waters that would come in. The areas there in gray and the red within the gray area have the other boxes with the arrows on them. Those areas were selected for thermal. Those were much higher levels of impacts, generally closer to the center of the site, and also included the DNAPL area. So it was a more complicated area, and we got costs from vendors to do these multiple different ways, and the thermal was less expensive than the other remedies that we priced out for those areas. Not sure if you had another slide there for me, or if that was, yeah, okay, good. Yeah, so this gives a little bit of the numbers, some of the ranges, some of those different alternatives we were just talking about. So we looked at it a few different ways. One was to do thermal for all 12 areas. There's some others that aren't included in here. We looked at doing excavations of all 12 areas, and those prices were extremely high. And then we looked at in situ and ex situ, ChemOx, along with some other options, and ultimately decided to do, like I mentioned on the last slide, some of the areas 1 through 5 with the thermal, and then the areas that are shallower, not as heavily impacted and closer to the property boundaries with soil excavation and disposal. So those were ultimately the 2B and 2C listed there were the technologies we chose for this specific project.
Very good. Thank you so much. Now I have a question for you, Chris. Essentially, you've been here 18 years, and can you give us a little overview of the value engineering we've done and what we've been doing to try to get our cost of thermal down?
Yeah, so with any new technology, you learn things as you go, and we certainly have learned a lot over the past 20 years. With any technology, you try to get the most value out of the infrastructure you install. Of course, there's a point of diminishing returns with electrode spacing, electrode diameter for certain soil types and conditions. Those are all things that have been incorporated into our model over time, where we monitor things and see what works well, what works just okay, and try to integrate those or that knowledge gained into future designs and applications. Another big change is into the equipment. It became very clear 10 years ago that you needed to have flexibility in how you heat. And with electrodes, you do that with voltage. So all of our systems have a lot of voltage control built into them on an incremental basis. So whether an electrode is a single element, a double, a triple, you have the ability to have discrete control of all those intervals to really target heating. So you get better energy density control, energy density being the factor that controls remediation throughout the vertical and the horizontal footprint. So you can get more energy into the areas that have more contamination or just naturally pull more current. That is something that you have to build into these systems. They are not self-regulating. Another adaptation, there's a photo of one of our steam condensers. This is something that has changed greatly over the years, some materials of construction to be more user-friendly and less have less downtime. But also things like that the lower connex is basically a large insulating box. And we used to use the cooling towers, which are on top, as somewhat of a reservoir for water. Operating in cold climates became a problem, so we designed them so they're constantly draining. and there's nowhere for that water to sit and be exposed to cold weather to where it could freeze and cause prolonged downtime. Obviously, in the Northeast or the Northwest or the Midwest, you know, you can get blizzards that come through that can really ruin your day. So we adapted the equipment to deal with those conditions, and that integrated thermal protection is something that has saved us a lot, because we do a lot of work in the Northeast where cold weather is definitely an impact. The other big thing is standardization of construction and design. Um, you know, there's a standard application, however, it has flexibility built into it. We have a fair number of sites where the goal of the project is to install it to refusal, and refusal can vary throughout the site. So the electrodes can be designed on an as needed basis as they're drilled. There's a lot of coordination between the engineering team and the field team, but we've developed a good system so that any kind of adjustments to the electrode footprint can be made on demand and not slow down drilling, because, you know, you're putting in 2 electrodes per day per rig. Sometimes there's up to 4 or 5 rigs on a particular site. There's a lot of moving parts, but we've become good at managing that. Some of the other things to keep in mind if you regarding keeping the price down is, you know, when you go out to bid, make sure that all the contractors are designing or they're giving their proposal for contractual guarantee for performance criteria. We prefer soil or groundwater specifications because that's the real risk driver. Where is the mass? This makes sure it's out of the matrix so that the risk has been, you can verify the risk has been removed. So whether you're going to do a guarantee or not, making sure that the conceptual design meets that criteria is very important. You know, scope split and risk sharing, depending on the client or the situation, working with the thermal vendor to share those risks and to put those in to the party that is best suited to manage them is a good way to save money, because when you get away from the raw, you know, materials and labor that go in, the amount of risk that gets transferred from one part to the other can significantly impact price. So working with the thermal vendor and being collaborative has really lowered the price for a lot of these big sites, versus just going with a very kind of rigid box. You can get creative and certainly save everybody a lot of money and time. There are a couple things to avoid. You know, we typically use cooling towers to cool the steam as it comes out of the ground so the vapors can be treated. Chillers are sometimes specified, and while chillers do a very good job at what they're doing, they are very expensive. They require a lot of energy. And so there's not just the energy usage, there's the infrastructure you have to put in. So if you're putting in a 2 megawatt service for a particular remediation, you would have to put in a 3 or 3.5 megawatt service just to power that chiller. So it's a very expensive option. Sometimes it's required, but not always. So figuring out a way to use a cooling tower and that heat of evaporation you get from it is very, very, it helps lower the cost. And sometimes we get requests for non-specific treatment goals or volumes. They just kind of have this generalized amoeba or block, and a lot of times that's a scaled up version for what they actually want, and the cost can balloon on them, and what ends up going back to the end user can be a little bit of a shock. So, you know, kind of doing your best to define the treatment volume, and also building in a cost for growth or a retraction. You learn a lot about a site when you start putting in electrodes and TMPs. So being able to say, okay, well, this area isn't as contaminated as we thought, or, oh, wow, there's a whole lot over in this portion of the treatment area. We may need to put in some additional electrodes. Building in the cost of that growth into the contract can save you a lot of money. And you know, QRS's preferred model is to contract on energy. You know, we we look at a treatment volume or remediation, a goal, come up with the amount of energy application it takes to achieve that goal. The risk of the time it takes to do that is placed on us, incentivizes us to move as quickly as possible. Time and material contracts can get a little tricky because if a site is underperforming from a heat, whether it be conductive heating or energy application with the electrical resistance heating, is borne by the end user, which isn't really where it should be borne. So we really recommend against T&M contracting outside of designs, portions of design. Lump sum contracting for design on the whole is a good thing, but sometimes there's electrical help with electrical needs or negotiation with regulators. Portions of that are good for time and materials.
All right. So Tom, I know you managed a very big, significant site recently, and my next question to you would be, can you give us a few examples of cost savings or value engineering decisions that help kind of control the spend on a large site like that?
Sure, yeah. And Gorm, I have a few of them here. So the first one, I'll start with the largest dollar item. And I think most thermal vendors like to see a preliminary design investigation, whether they do it themselves or the consultant or the client does that in advance. But it's a critical step. In this case, like I said before, we already had a good conceptual site model. We've done MIP, LIF, along with traditional site investigations. But then once we'd narrowed down what areas we were going to treat and how we were going to treat them, we wanted to look at obtaining more data in order to get the most accurate bids possible and only remediate what you need to, but on the other hand, make sure you remediate enough. So it's really defining that. So in this case, we saved over $3 million on this project. So I've said this before, but I think I was at a Battelle conference several years ago, and they were summarizing all the Superfund projects. And they said from a site characterization perspective, at the hundreds of Superfund projects that they had evaluated, over 85%, or 80 to 85% of the site investigation dollars spent are spent after the first remedy is implemented and fails. So you want to make sure you have the right scope of work and you don't have scope creep once that project starts. So I think those are some of the critical items. This specific project saved $2.2 million on the rebidding with the thermal vendors after we'd done this preliminary design investigation. Saved about $900,000 on anticipated electrical usage based on the first bid and the actual usage. And then saved over $100,000 on the soil excavation, which was the other area I was talking about previously. So those were significant numbers. And just really quickly, what does a pre-design investigation entail? I've got another slide in there which talks about what that is and how it differs from a traditional site assessment. You're really narrowing in on that area you want to treat. Frequently, you'll do a grid pattern of that area. You may collect traditional grab samples or composite samples. Composite samples can be very good, for instance, if you're looking at doing soil excavation and you want to know, is that 0 to 5 foot interval, is that going to have to go off as has, or is it just from the 5 to 10 foot interval? So you have a good handle up front, what's going to need to go off as has versus non-has. Do some of that waste characterization up front. If you're looking at thermal, for instance, there's a number of other targets you're going to want to look at. Again, defining lateral vertical extent. Are there impacts outside of our remediation area that are going to impact it? And then some of the specific contaminants that you might not do as part of your traditional investigation, regardless of what remedy you select. You may want to add in there fraction organic carbon, electrical resistance of soils, water content of soils, some parameters like that can be very important from a thermal standpoint. Yeah, if you're doing chemox, you're going to look at some other types of pre-design data collection, but based on what remedy you select, some of those items can be very helpful. So I think that was the biggest significant cost savings, but we do have some other ones on this project as far as operations go. This, going back to what I was talking about, we were able to eliminate 3 of the areas altogether that we had planned on remediating out there because we, after doing more detailed sampling, they really were no longer considered source areas. In some cases, it was based on MIP readings as opposed to actual soil concentrations. In other cases, it was just a very minimal de minimis impacts. And then two areas that I really wanted to mention here is just that we had planned on doing soil excavations. And after doing the pre-design investigations, they either grew in extent or in concentrations. And the thermal bids for those areas ended up coming in significantly less than the excavations based on concentrations, lateral extent, and then vertical extent, the amount of liquids in the one area there that I mentioned previously that had the DNAPL. So I wanted to mention that. And then if we want to go on, I have two other cost savings areas. In this case, the cost reductions through vapor treatment. This was, for this project, we had a couple of different ways to treat the vapors. And one was basically using an RTO or the regenerative thermal oxidizer along with a more traditional vapor phase GAC. And those were set up to handle kind of two different areas of the site. So the RTO handled the most impacted intervals that had the DNAPL and the very high concentrations of the chlorinated VOCs. And then the more traditional GAC or vapor phase GAC was handling the other areas that had significant VOCs, but not as high concentrations. So one thing to keep in mind on this is permitting for your specific site, depending on where it's located per county, per state, or per country. For instance, this project was in Indiana. Projects in California may have more stringent air permitting standards. So it is a site-by-site evaluation you have to do. If you're in Canada or Australia, those numbers may be considerably different also. So take that into consideration. All the permitting requirements, not just vapor and air.
So real quick, I don't know if anyone can see my mouse, but this is the oxidizer over here, right? And that treated the high concentration DNAPL area. And here's a carbon. If we had to build an oxidizer for the whole stream, it would have been 4 times bigger than this one or something like that, and used a lot of gas. That's one of the technical reasons why it made sense to have 2 different treatment trains for vapor. Yeah.
One other real quick note on that is just at the end of the project, we were able to stop using the RTO altogether because the concentrations were very low and just operate one of those 2 remedies or treatment methods.
Yeah.
Oh, yeah, here was another one also. This was the third item that I had mentioned as far as the cost savings. And this is basically how you sequence on the project. And area 1 is the massive area on the right of the screen there. And area 3 is on the kind of the center or southern portion, southwestern area. Those were the 2 most aerially extensive areas of our site that had significant impacts. The most electrodes are in those 2 areas. The most power is going to those 2 areas. So a lot of money is being spent on those areas. And we were able to, through a sequencing standpoint, eliminate those 2 areas first. So that was a positive thing because we reached project goals based on hot soil sampling for those 2 areas. And over half of the electrodes and the power were able to be shut down relatively early in the project. To really spend the energy going forward on the areas that had higher levels of impacts in the smaller areas of the site. Those are my kind of 3 takeaways from this project on some areas that I think we're able to save money. Again, that preliminary design investigation was the biggest cost saver. This was probably the second biggest cost saver though.
Thank you very much. So, Chris, I know you know of another site in California where vapor treatment was also one of the sticky points, right? It's more and more difficult to get an oxidizer permitted for a high mass site in California. Can you share a little bit of that experience with us, please?
Yes, so TRS owns a self-contained steam regenerative GAC system. The photo of it is on the screen. The stainless steel vessels you see there are just, I think they're 1,800 pounds each of carbon. And after they load, they're regenerated with a boiler that is part of the system. There's a cooling tower that accompanies this, and what you can't really see it on the right-hand side, but there's also a decanter. So as the steam or as the stream is the VOCs are stripped from the GAC, we take those VOCs and we recondense them into a liquid. So you actually get the NAPL back. So that can be a cost, but it also provides a lot of assurance that stuff has been removed. A little bit of water comes out with that as well, which can get treated within the existing system. But this saved a considerable amount of money. The site that this is at right now is incredibly impacted. Tens of thousands of pounds of mass, and we're basically, we did a pilot test. It worked very well, and we've expanded to the full area, and we're just trying to take the edge off the mass load, because SVE actually works here to continue to get contaminant out of the ground. So this is the right situation for particular contaminants. You know, if sometimes we use it in sites that have where the contaminant has poor loading to GAC. We're using traditional GAC. You just couldn't get the vessels in quick enough. The recycle time on this unit can be, I think, about 7 hours. So every 7 hours, you can have a new vessel to absorb the contaminant, because they're loading at such a relatively low amount per volume. The other efficiencies that we've gained is really, while the cost of thermal treatment in general is clicked up over the years, due to improvements in the application of technology, I would say that the targeting of the important soil volume for remediation has improved through better delineation, better modeling. So that cost has probably gone down. It's kind of a subjective evaluation, but we definitely feel like this is being used where it needs to be, by and large. In situ thermal can get any site to MCLs that you want it to. However, that can be very expensive. It's a lot of time. It's a lot of energy. We can drive the concentration down to a slightly higher goal and use some other method to finish the site off. Is usually a better application of thermal. It is a big, powerful sledgehammer, and using it more appropriately is a way to lower overall costs. Some of the other things we've done, as I think all the thermal vendors, we've played around with electrode and heater spacing, diameter, wattage per foot. All of those things are continually evaluated. For a period of time, we tried to push electrodes out, well past 20 feet to get better economy of getting power in the ground, and we just found it just didn't work. At the end of the day, the cost of struggling to achieve the remediation goal is far greater than the additional infrastructure. So we have brought our standard spacing back down to try to get the better result, because ultimately that's what matters. One of the things we've adapted in our new heater technology is the ability to change it in the field. We can change wattage on a linear basis within the heater itself in the field without the need for any kind of expensive retrofit, and using different materials to use less energy. If you're targeting an area 30 feet below the surface, you have what is called a cold pen, where you're not really remediating, but the heater itself does produce heat. We use different materials to lower that energy cost, which can be significant, and is really decrease the amount of total energy and power infrastructure for thermal projects where they've been used.
Wow. So I just want to remind people listening in, you can type in questions under Q&A. We have very few so far, and that's why I'm allowing us, a little more time to answer the ones we have had prepared. So if you have one, type it in there and send it, because we will definitely look at it. I will move through a couple more questions until of our own, until I see more questions come in from you guys. I have one for you, Tom, and that's essentially that big project you mentioned. I know that you asked vendors for quotations several times and eventually had to select one. Can you tell us about, even with the detail you provided, how was the spread in the proposals you got, and how did you decide what to do?
Sure. Yeah. That's a good question, Gorm. And we consider that on every project as far as how we're going to bid it and then how we're going to compare bids also. So that's a very important process. And ultimately, when you're getting those bids, you want to be able to compare apples to apples. And a lot of times you may not have apples to apples. But the way to do that, the best possible way is to provide as much detail to the bidders or the vendors as possible. So a detailed bid sheet, provide them with a detailed conceptual site model, as much data as you have possible, boring logs, analytical results, any information on the soils themselves, the hydrogeology, a detailed conceptual site model, what contaminants of concern you may have, what are the target cleanup goals, which is a huge one, what's the schedule, how quickly you need to clean up. Certainly, a lot of these areas, ultimately, if you are looking for different guarantees on that, let them know up front and have that included as part of the bid. So I think those are all important items. However, provide all this, you can still get a significant spread with your vendors. So ideally, you want to see them within 10% of one another. If you do that, you feel like we did a pretty good job of providing that information to the vendors because they're very close on their bids. We do frequently see a much greater spread, 20 to 30% spread. You asked on this specific project, how did they come in? Our first round of bidding on this, I think we requested 5 bids and received 3. The 3 bidders, all very highly respected companies, have a lot of experience in this. 2 of the bidders were very close to one another. And as you mentioned, it was a large project, significant project. Those 2 bidders were around $10 million on their end of it. That does not even include electrical usage. The 3rd bidder was about $3 million more than that. And $3 million is a lot of money. Percentage-wise, it's still right in that range. It's in that 20 to 30% common spread that you see. It's just a bigger dollar item, so it stands out more. But those are some of the areas we look at. And then ultimately, once you've received those bids, you try to figure out what's separating them. In this case, I think the biggest difference was, I guess, being more conservative or assumptions that were made on losses of energy, what you would need to have at the surface to prevent losses of heat. So I think that was the biggest difference in this case.
Very good, thank you. And I'll transition to now to a question from Eric Zimmerman. Very good one. It's essentially a question: if most of your mass is down below and there's clean, I'm rephrasing it now, there's some clean soil on top that doesn't really need treatment. Can you just treat down below, or if you heat down below, don't you just push the mass up and it condenses in the top? Chris, it's probably a question for you, as much as for Tom, but I've had the same thought actually for this exact site, that some of the part of the site, the upper six feet were not that contaminated, and then the treatment happened from 6 feet and down. What did we take a little bit of a risk because the electrodes didn't heat the top 6 feet? What was the decision for the thermal design, and what did you do in the couple of areas where maybe some contamination was found shallow at the end?
Yeah, so it's obviously situational. As long as you can get vapor recovery in that upper area, we typically don't have to come all the way up to grade, where you just target the impacted zone. The one thing you do have to do is come all the way to the water table. If you're trying to heat a portion below the water table, as soon as it hit that cold water above it, you would get that condensation issue that was mentioned. And also in high plastic clays, that can be somewhat of an issue, where you'd want to bring it all the way up just to make sure it gets that pathway. And the technologies are a little bit different. There's more vapor recovery built into ERH than there is TCH. or thermal conduction heating versus electrical resistance heating. But they can both use, basically chimney wells. You've got to give the VOCs a way to get out. So yeah, it really depends on the site. Some sites you have to insulate the cap and bring it all the way up, and sometimes the soil is permeable enough where you don't. There was a situation at the site Tom is mentioning where there was a little bit of impacted zone in the shallow zone, and it was far cheaper to dig the very small area than to try to continue to heat it with thermal. And that was a cost benefit evaluation that was done during the remediation.
So to finish the site off, you have to excavate a couple of little hotspots at the end. Is that right?
We did, and they were both relatively small areas and shallow. And the question going back to the concern with possibly moving mass from the primary source zone up to the soils above that that are not impacted as much. We had that concern, so we did do hot soil sampling throughout to make sure that wasn't happening, or if it was happening, to be able to deal with it. These two areas, I don't believe were associated with that process. It was, we had elevated concentrations there. There may have been some additional via steam and vapors coming up and then adhering to those soils, certainly. But ultimately, these two areas, we were not able to hit temperature goals because of infrastructure in the area, subsurface infrastructure. And ultimately, these were both small excavations, not very expensive to do, far less expensive than to continue to run the thermal with the minimal benefits we would receive by continuing to run it.
Mm-hmm. Yeah, and over the years, the concern of shallow recondensation is it's a pretty common concern, and usually within the sampling protocol, monitoring is done to make sure that didn't occur. TRS has done over 150 projects. There've only been one or two where this was actually a situation that had to be remedied. So it certainly is possible, but it's not as common as I think a lot of people are believe it to be.
Yeah, I do believe, without sharing too much, I do believe that other proposal, which was $3 million higher, included heating all the way to the surface. So that may have been one of the differences. So that additional $3 million would have taken away that risk of having to excavate a couple of hotspots. But can you tell us roughly, how much was it? Was it less than 3 million to do those hotspots at the end?
I would say yes, it was significantly less than $3 million. The one area was an excavation down to 5 feet, and it was a 20 foot by 20 foot area. The other was similar in area down to 10 feet. Both were able to go off as non-haz, so not a significant cost.
So you have not regretted?
No,
No,
in this case.
Good, thank you. A few more questions came in from the audience. We'll take another 3-4 minutes. One of them is about sustainability. And I know this webinar is about the cost of thermal remediation, but some of us believe that soon things related to sustainability will have much more impact on what we do. Not just dollars per kilowatt hours because there's CO2 emissions, but an overall kind of life cycle analysis of projects. And when you have alternatives for a site, either excavation versus in situ thermal versus chemox or whatever it is, if you know what the outcome is, you can actually make a life cycle assessment of it and a sustainability analysis and determine which one has less impact on the environment for the same benefit. Is that something you're thinking about? And if it isn't, will it soon be?
Tom, I don't know if you want to go first.
Go ahead, Chris.
Okay. I mean, inherently, we try to reuse as much as we can. All the supply cables, all the equipment, sometimes vapor recovery piping, depending on the situation. You try to reuse as much as you can just because for the economic reasons. We have we've built, we have a warehouse in Indianapolis, Indiana, where we store our equipment, do maintenance, store excess materials, things like that. And there's a whole inventory system where if it's worth bringing back and reusing, then we will try to do it. There are some things that go into the ground that aren't recoverable. The electrodes are not recoverable. The heaters are, and we try to reuse the materials, the heating element itself, as best we can. They usually last 5 to 10 years because they are pretty robust metals. But some of the things that go in the ground you can't get back out, or the cost of doing so would be too much. But yeah, I think I agree with the question that sustainability is something that will be in the future, and trying to increase that will be part of our analysis going forward.
Yeah, I could just add a couple of additional comments on that too. It's just people may look at it as a negative from a sustainability because of all the energy you use. But there are, as you mentioned, some of the positives there. Reusing cables, for instance. The miles of electrical cables that we used on this project were mind-boggling. So to be able to reuse those over and over, it's not just a one-time use. So that's certainly noteworthy. We also did look at it from some comparisons to other technologies, and it favored pretty well with some of the other dig and haul, for instance, when you're having so many vehicles back and forth and all the fuel it takes to run those vehicles back and forth, all the loads of soil and water. So it's worth looking at, and it is a lot of energy to use, but it can be as sustainable or more so than some of the other options.
Very good. And I can add to that sustainability and resource usage, and whether the metals we use are replenishable, or whether it's nickel that we don't have that much of left, for instance, goes into all of our R&D and our value engineering that occurs, at the sites, but also at the warehouse in Indianapolis. Testing is being done, try to find basically ways of completing boreholes with less cement, because cement is a big sinner when it comes to CO2 emissions. When you bake clay and lime into cement, it uses a whole lot of energy. So the CO2 footprint for that is really poor. Stainless steel and nickel alloys with all the nickel, and we have to try to minimize the use of that. And that all goes into basically our testing program and our value engineering, how we're constantly looking for more effective and also more sustainable options and testing them, making sure they're fine before we put them in the field. I think the time is up now. It's never too late to ask questions to the two experts. You can see their email addresses here. Were a couple of other questions that were more kind of technical to the slides that we will answer by email after this webinar. We hope to welcome you back in September when the next webinar will be. We don't have a firm date yet, hoping it will be September 10. And the title of that one will be more historic, the last 20 years of thermal treatment. David Fleming will be our TRS expert, and he'll be joined with Kira Lynch, who has been a regulator and an Army Corps person for the last 25 years, speccing thermal and now overseeing thermal remediation. So she'll be on the next panel as well. We hope to have you back. And thank you very much for attending today.
Thank you.
Thank you.
Yes. Thank you, experts.